Hello again. Today we're going to be talking about how to define continuity at a point. So first of all, the definition of continuity has three parts to it. We can say that a function f is continuous at the point where x equals a if three things are true. The first thing is that the limit as x approaches a of the function has to exist. The second thing is that the function has to exist at that same value of a, and the limit and the function value have to be equal to each other. So if all three of those things are true, then we can say that the function is continuous at that point. So if the limit doesn't exist, that's the first condition. And if that is false, then what we have is we have a jump discontinuity, or maybe we have a vertical asymptote, or maybe we have a combination of the two. If the limit does exist, but the function doesn't exist, then what we have is what's called a removable discontinuity. We informally call that a hole, but that's just when we're talking about it. When we write things down as part of a solution, we write removable discontinuity. Also, if the limit and the function do exist, but they're not equal to each other, that's also a case where we would have a removable discontinuity. All right, so here's an example. If we have this function, it is a piecewise function with three pieces, and we wanted to know if the function was continuous at x equals 3. So we need to check to make sure that all three conditions are met. If any of them are not met, then we can't say that the function is continuous at x equals 3. So the first thing we're going to look at is, does the limit exist at x equals 3? We need to look at this limit from the left and from the right, and we have different pieces for each one. So if I'm looking at x approaching 3 from the left, I'm going to take the limit of my function using the first piece, because that's where x's to the left of 3 are going to be plugged in. So if I factor that piece, I'm going to get 2 times x minus 3 over x minus 3. The x minus 3's will divide out because, remember, we're not plugging in x equals 3. We're plugging in values that are close to 3. So we're not going to get 0 over 0. We're going to get something where the x minus 3's cancel, and I'm going to end up with 2. Now, if I do the same thing and I look at x values that are a little bit bigger than 3, then I'm going to use the bottom piece, and I'm going to look at what happens as I plug x's close to 3 into x squared minus 7. And when I do that, the y values actually approach 2. Okay, so since I got 2 for the left-hand limit and the right-hand limit, then the limit does exist, and the first condition is met. So I'm 1/3 of the way through saying that the function is or is not continuous at x equals 3. So I'm going to keep going and figure out if the second condition is met. I need to figure out whether the function exists at x equals 3. So I need to look at the middle piece, because that's the only piece that's being used if x equals 3. So this is defined. F of 3 is actually equal to 2, so the function does exist. And now the last condition is, are the limit and the function equal to each other? Well, the limit was equal to 2 and the function was equal to 2, so yes, the limit and the function are equal to each other. That's the final condition to show that the function is continuous at x equals 3. So yes, I can say that the function is continuous at x equals 3. So that's how I show continuity at a point. Those are the three conditions that you have to follow in order to do that. If you have any questions, please let me know, and I will see you tomorrow.